Right, when we think about computer data, our minds usually jump to the simple stuff, numbers, letters, a simple true or false. But the real world is so much more complicated than that. So in this explainer, we're going to dig a bit deeper and look at how computers actually build a rich understanding of our world, right from the ground up.
I mean, just think about it for a second. Your social media profile isn't just one bit of text, is it? It's a name, an age, a list of your mates, photos, dates, all of this stuff bundled together. A simple integer or a string just can't handle all that on its own. So how on earth do computers manage it?
Well, the answer starts with something called custom data types. You see, basic data types are a bit like individual Lego bricks. They're useful, for sure, but they're limited. If you want to build something meaningful, like a model of a car or a person, you have to combine those bricks into a proper structure. And that's exactly what we're talking about here. And the tool that lets us do this is the user-defined data type. This basically lets a programmer invent a brand new template, a kind of blueprint. This blueprint groups all the different bits of information about a single real-world thing, like a student, into one neat package. It's how we tell the computer what a student record should actually look like.
This table here shows a really great side-by-side comparison. On the left, you've got the individual Lego bricks we were talking about, an integer, a string, a date. But on the right, you can see the finished model, the student record. It pulls together all those basic types into a single logical structure. It's a lot like filling out a form where each box, name, date of birth, all belongs to one person.
Right, so we can now create these complex records. Fantastic. But what happens when you've got millions of them stored in a massive file? How does your bank find your specific account record instantly out of all its millions of customers? This is the digital version of finding a needle in a haystack.
Well, there are two main ways to go about it. First, you've got sequential access. This is like reading a book from page 1 until you find the chapter you're looking for. It's fine for jobs where you need to go through every single record anyway, like when a company sends out monthly bills to everyone. Direct access, on the other hand, is like using the index at the back of the book to jump straight to the correct page. This is absolutely essential for any real-time system, like a cash machine that needs to find your balance right now.
Okay, let's make this a bit more real. Imagine you're at the school office, and they need to look up your details on the system. Are they going to scroll through every single student in the school, starting from the A's? Of course not. That would take forever. They need direct access to get to your record immediately.
So how does this magic of jumping straight to the right record actually work? Well, it's not magic, but it is a very, very clever technique called a hashing algorithm.
And actually, it's a pretty straightforward process. You start with a unique piece of data, like your student ID number. You feed that ID into this special mathematical function, the hashing algorithm. The function then crunches that number and spits out a physical memory address. That address is the exact location of your record on the hard drive or SSD. So the computer can just go straight there, no searching required.
Okay, let's switch gears for a bit and tackle another fundamental problem. We know computers are built on binary, ones and zeros, which is perfect for whole numbers. But how on earth do they handle numbers with decimal points, like 3.14? Or really small fractions like minus 0.05.
They do it using a system called floating point representation. This is actually very similar to the scientific notation you've probably used in maths or science class. Every single number is broken down into two key parts, something called the mantissa and something called the exponent. And this slide breaks down their jobs perfectly. The mantissa holds the significant digits of the number itself, in this case 11010. The exponent is the instruction that tells the computer where to move the binary point. For the number 12.5, the exponent 100, which is 4 in our normal base 10 denary system, tells the computer to shift the point to get the correct value. By combining these two parts, computers can represent a massive range of numbers. But there's a little catch. A single number could actually be represented by lots of different combinations of mantissa and exponent. And to avoid complete chaos and make sure we're getting the most precision possible, computers use a standard format. This process is called normalization.
The whole point of normalization is to standardize everything. It adjusts the number so that for any positive value, the mantissa always starts with 0.1. This makes sure we're not wasting any precious storage space on leading zeros, and we can use all the available bits for the actual digits. This gives us the best possible accuracy.
And you can see it in action right here. On the left, you've got an unnormalized number that's wasting space with those leading zeros. So by shifting the mantissa 2 places to the left, we get the tidy normalized form on the right. And to make sure the value stays exactly the same, we just adjust the exponent down by 2 to compensate. Same number, just stored in a much more standard and precise way. So, to wrap up, it's really important to remember that all these systems we've talked about involve trade-offs. Trying to represent the infinite complexity of real-world information on a finite machine is, well, it's never going to be absolutely perfect.
With floating point numbers, for instance, you can run into a few problems. An overflow error happens if a number is just too big for the computer to store. An underflow is the opposite. The number is too incredibly tiny, too close to zero. But the most common issue is rounding errors, simply because some ordinary decimal fractions just can't be represented perfectly in binary, which leads to a tiny loss of precision.
So, from how a character is designed in your favorite game, to how fast a search result pops up, to the accuracy of a financial calculation, every system you use is balancing things like precision, range, and speed. The next time you're using an app, just have a think. What compromises might be happening under the bonnet? Thanks for tuning in.